Download the biggest AI model you can find, 15 gigabytes. Now try to run it. Double-click. Nothing happens. A model is not a program. It is a box of parts, and the thing that assembles those parts decides almost everything about how fast your AI runs.
This is the map of everything between a downloaded model and an answer on your screen. 4 phases: load, prefill, decode, serve. Today is the first box, loading. It looks boring. It decides whether your model starts in 10 seconds or 10 minutes.
Open the folder of any downloaded model and you get something like this, a handful of files, and none of them are executable. The giant one, usually called safe tensors, holds the weights, billions of numbers, and nothing else. No logic, no instructions, just numbers packed in a known layout. The small one, config.json, is the assembly manual. It says how many layers the model has, how many attention heads, which attention variant, how big the vocabulary is. The entire architecture described in a file smaller than a photo. Then the tokenizer files, the dictionary between your words and the model's numbers. So what you downloaded is a flat pack, parts and a manual. Nothing in this folder can run. Something has to read the manual, assemble the machine in memory, and operate it. That something is called an inference engine, and your choice of engine changes everything.
The engines are the builders: llama.cpp, written in C++, vLLM and SGLang, mostly Python, TensorRT, compiled ahead of time for NVIDIA hardware. Same parts, different builders, very different machines at the end. Here is where your instincts betray you. C++ is famously fast, Python is famously slow, so the C++ engine should win, right? Measured on real workloads, the mostly Python engine sometimes beats the C++ one at generating tokens. Hold that thought for the whole episode, because if the programming language is not what makes inference fast, something else is, and that something is the actual subject of this series.
Those 15 gigabytes of weights start on your SSD. They are useless there. To compute anything, they need to reach the processor, and computers have a strict hierarchy for that. Disk, then RAM, then, if you have one, GPU memory. Each step up is smaller and much faster. The naive way to load a model: read the weights from disk, copy them into RAM, then push them onward. Notice the word copy. For a while, the same 15 gigabytes exist twice. On a 32 gigabyte machine, one model just ate most of your memory before doing any work. Loading, it turns out, is not reading a file. It is a logistics problem.
The fix that most engines use is called memory mapping, and the idea is old, elegant, and borrowed from the operating system. Instead of copying the book, the OS lends you pages. The engine tells the operating system, "These weights live on disk. Here is their layout. Give them to me when I actually touch them." Pages load lazily, on first use, not eagerly up front. Start time collapses. And the loan works both ways. RAM is contested space. Your browser wants it too. So when memory gets tight, the OS quietly evicts pages of your model. Touch them again, and it reloads them from disk like nothing happened. What does that eviction cost? Say 5% of a 15 gigabyte model gets evicted. That is 0.75 gigabytes. Over a modern NVMe link at roughly 7 gigabytes per second, reloading it costs about 1/10 of a second. That is the trade, a barely noticeable stutter in exchange for instant starts and a machine that stays usable. Now the payoff on 10 seconds versus 10 minutes. Load the same model in llama.cpp and you can be generating your first token in seconds. It memory maps aggressively, assembles little, and starts serving you, one user, immediately. Load it in vLLM, and startup can take minutes, not because it is badly written, because it is building a different machine. It initializes schedulers, allocates memory pools, prepares for hundreds of simultaneous users. It is not assembling a bicycle, it is assembling a bus depot. Same parts, different builder, different machine. Which is the honest answer to the paradox from earlier. The language was never the point. What the engine does with memory and what scale it prepares for is the point. There is one more door in the loading room. Those 15 gigabytes do not have to stay 15. Quantization shrinks the weights to lower precision,
which is why the same model appears on Hugging Face in a dozen sizes with cryptic names. I made a full episode on exactly how that works and what it costs in quality, card on screen. For today, the one thing to hold: smaller weights change every number in this episode. Less to map, less to evict, less to reload. Loading and quantization are the same logistics problem.
Zoom back out. The model is in memory, assembled, mapped, ready. And nothing interesting has happened yet. No prompt, no token, no answer. Everything you just learned exists to feed the next 3 boxes: prefill, where your prompt gets read; decode, where the answer gets written 1 token at a time; and serve, where one machine does this for thousands of people at once without anyone waiting in line. Next episode, the pause and the typing. Because reading your prompt and writing the answer are 2 different programs, one of them wastes the most expensive chip on Earth, and your API bill has known it all along. A model is a box of parts. Now you know the assembler. Next, you watch it work.